Okay, welcome back. We'll continue with our treatment of equilibrium problems. And remember how we set about doing this. We introduced this idea first of a functional and then talked about what it means to take a derivative of a functional with respect to a function. And in the process, we introduced this new object that we called a variational derivative. Okay, so that's as far as we got last time. And we got as far also as saying that if pi is a functional of the displacement field, and if this is the free energy functional, right? U is the displacement. U is the displacement field. Then we said that the variational derivative is this one. We decided to denote it either as delta pi over delta u or d pi with respect to u. And we said that this derivative is defined as derivative with respect to epsilon of pi evaluated at u sub epsilon. Okay, we compute this derivative with respect to epsilon, and then we set epsilon equals 0. And we motivated this nicely in the context of a one-dimensional problem, right? Just to be able to fix ideas, and because we're able to actually sketch out things for 1D problems. Okay, we'll go ahead with this idea. Now, so where we are right now is that we now know how to compute the derivative of our free energy with respect to a function, right? In particular, the displacement function, or the displacement field, which is a function defined over the entire domain. Okay. But we're not yet done. Remember, when we talked about equilibrium, we said that equilibrium corresponds to an extremization of energy. And we need to extend that idea of extremization to this this variational derivative in order to be able to talk about equilibrium. Okay, so let's just state that and then go on. Okay, but equilibrium states correspond to extrema of pi with respect to u. Okay? Now we take the approach that we know from traditional calculus, which is to say that extrema of sufficiently smooth functions are reached when the derivative, the first derivative, goes to 0. Okay? So likewise, we're going to say that assuming that pi is a sufficiently smooth functional of the function u, we will say that an extremum is obtained when this variational derivative, as defined here, vanishes. Okay? So what this says is that at equilibrium, we have this variational derivative equals 0. Okay? All right. So that is the requirement we have at equilibrium. Now, what we're going to do is, without spending too much more time, on this, we're going to go ahead and apply it to the particular free energy functional that we constructed in the previous segments for our problem of nonlinear elasticity. Okay, so we will now go ahead and apply this idea to pi of u for nonlinear elasticity. Right, let's get on with it then. So we start here, okay? So, what we have is that we are given pi of u, and I will again write it out explicitly. It is the integral over omega naught of psi, written as a function of f, okay? But it's a function of f, yes, but then we know that f is also obtained from u in this manner. Okay, so it's psi integrated over the volume minus the work done by the body force okay. Let me see, I think we are deciding to do this all in the reference configuration, so we have J BF here. That's right. dV minus integral over the traction boundary of the work done by the traction, T dot U dA. All right, that is what pi is. Okay, and we can see that each integrand here does indeed depend upon the displacement field u, right, upon the displacement function u. All right, and now we proceed as before, as we've laid out in the previous segments, which is that we define variations. Okay, and in order to do that, we say that for u belonging to the space S, which you recall consists of u such that u satisfies the displacement boundary condition on the displacement boundary. Okay, for these kinds of displacement fields, consider variations which we will write as u sub epsilon equals u plus epsilon w, where epsilon just belongs to real numbers, right? Epsilon is just a scalar, and w belongs to V, right, a space of functions, such that, how is V defined? V consists of all functions W which satisfy the zero boundary condition, right, or the homogeneous boundary condition on the displacement boundary. Okay, and let me just recall for us that u and w are vectors. Okay, so when I say that u belongs to S, we're talking about the type of function that u may be, right? When we talked last time about how they could be polynomials or exponential functions or trigonometric functions or whatever. Same thing for W, right? And what we've done here is also incorporate their the boundary condition on U. Okay, and the same thing for W, right? But W satisfies the homogeneous boundary condition. We talked about why this makes sense. Okay, because the idea is that when we are carrying out variations now of this type, we ensure that we do not violate the original displacement boundary condition. Okay, and this happens when W is homogeneous on the displacement boundary. Recall, however, that when we say that U and W belong to R3, what we're saying is not so much, we're not saying anything about the functional form of U and W, but that they are vectors. Okay? All right, so this is what we're doing. We've set up the types of variations we want to consider. All right, now let's go ahead, write out the variational derivative and its extremization. Okay, so what we're saying is that for equilibrium, or at equilibrium, what we have is the variational derivative of pi with respect to u, okay, which you recall by definition is this quantity, dd epsilon of pi evaluated at u sub epsilon, where we defined this field u sub epsilon, right? Okay, at epsilon equals 0. Okay, so all of this right-hand side is the variational derivative. Okay, but we want equilibrium, right? So we want to extremize this derivative. So we say that this derivative has to vanish. Okay? All right. So this is the condition we have, and what we will do now is just go ahead and apply it. Okay? So, so let's first calculate this. So let's first, let's go ahead and just calculate it. So what this implies now is that we have dd epsilon of pi evaluated at u sub epsilon. Let's evaluate pi at u sub epsilon. It is dd epsilon applied to this entire integral, right? Or rather to the sum of integrals. In the first case, sorry, we don't have w there, we have psi. In the first integrand, we have psi, which is a function of this tensor, the isotropic tensor plus the displacement gradient tensor, dv minus integral over omega naught j vf dotted with u. Okay? Except that now I need to remember that we are now evaluating everything at u sub epsilon. Okay? Right? D capital V minus integral over the traction boundary of T dotted with u sub epsilon dA. Okay. Now, when we are working, and I need to close things here. Okay, right. I also need to remember that once we take this derivative with respect to epsilon, we then set epsilon equals 0. Okay, because this is what gives us the proper variational derivative. And then, because we also have an extremization, we want to set this entire left-hand side to 0. Okay, that final setting to 0 is what gives us an extremal, an extremum. Okay. Now, one more thing I want to do here is to remember that we have here for J times BF, we have a another symbol that we used, which is capital B sub F, which is the body force per unit reference volume. Okay, so this is the body force per unit reference volume. Okay, omega naught. And in computing this derivative, what we are going to do is to say that it is this quantity BF, which is given to us as a parameter. Okay? Okay, so this is part of the data of the problem. Okay, it's a known forcing function. Okay, all right. This is what we have to do now. Now, computing this derivative with respect to epsilon is actually a very easy task. This is because, first of all, our domain of integration, omega naught, is fixed, it being the reference configuration. And furthermore, when we write out u sub epsilon in terms of u and w, we observe that epsilon is simply a scalar. Okay? And therefore, taking derivatives with respect to epsilon is not difficult at all. Okay? So, the way this works is the following. First of all, it means that we can take those derivatives into the integral sign. Okay? Into the integral sign for each of these integrals. Okay? So, when we do that, we get the following. We get from the first integral, we get integral over omega naught. Now, we want to take derivatives with respect to epsilon here. Well, we just apply the chain rule, okay, because that argument under which I've just drawn a brace bracket is the argument of our strain energy density function. Okay, so we take we apply the chain rule, and what that gives us is the following. It tells us that it is derivative of psi with respect to f contracted with derivative with sorry. It's not a partial derivative here, it's a full derivative. Derivative with respect to epsilon of f sub epsilon. Okay? And this quantity that I put a brace bracket on is f sub epsilon. All right? That's what we get for the very first term, right, for the first integral. And likewise, we go on to the next integral. We get integral over omega naught. Now, because we agreed here that the data of the problem is capital BF, right, and that this is the body force, right, per unit reference volume, right, and this is the quantity. This is a known quantity, right? It's one of the forcing functions in the problem. So, when we take that derivative, it is BF dotted with dd epsilon of u sub epsilon d capital V minus integral over attraction boundary T dotted with dd epsilon of u sub epsilon dA. Okay? So this is how we take that derivative with respect to epsilon, and then we have to remember that once we take that derivative, we are going to have to set epsilon equals 0. Okay? And then the extremization step comes about when we say that that entire process that we've carried out, that entire derivative that we've carried out, and after setting epsilon equal to 0, itself is equal to 0. Okay? All right. Let's go ahead and do this now. This is not difficult at all because we observe the following, okay? Note that dd epsilon of f sub epsilon equals dd epsilon of the isotropic tensor, which is a constant, plus derivative with respect to reference position of u epsilon, but then u epsilon is u plus epsilon w. Okay? When we carry this out and we recognize that the order of derivative with respect to epsilon and derivative with respect to capital X can be interchanged, we get the following. From the first term, we get 0 because the isotropic tensor is a constant. But from the second term, we essentially get derivative of w with respect to x. Okay? Simply because it's the only term in there that has epsilon multiplying it. Okay? So we get this as the derivative with respect to epsilon of f epsilon. And then the next term that we have to compute a derivative of is actually even simpler because it doesn't even have that derivative with respect to x. It's this one. And that is dd epsilon of u plus epsilon w, which is just little w. Okay, we're going to use these in our in the last equation we had on the previous slide. When we do so, what we get is the following. We get, from the first integral, we get integral over omega naught derivative of psi with respect to f contracted with derivative of the variation with respect to capital X dv minus integral over omega naught bf, the body force dotted with w, dv minus integral over the traction boundary of the traction dotted with w dA. Now all of this evaluated at epsilon equals 0. Okay? All right. Now, where would epsilon be equal to, where would we have to set epsilon equals 0? Well, actually, the place that we would have to set epsilon equal to 0 would be here, because though I wrote this as derivative with respect to f, it is actually derivative with respect to, it's derivative with respect to f, but it is derivative with respect to f evaluated at f sub epsilon. Okay? All right. Okay, and then the extremum is obtained when we set all of this equal to 0. Okay, so this epsilon equals 0 has to be applied here. But that simply means that we have to compute this derivative with respect to f, okay, evaluated at epsilon equals 0, but then when we look up here, right, at the very first line that we wrote on this on this slide, we know that f epsilon evaluated at epsilon equals 0 would simply mean that here that epsilon has to be set equal to 0. Okay, so what we get now is integral over omega naught derivative of psi with respect to f, okay, evaluated at f, okay, contracted with partial of w with respect to x dv minus integral with respect to omega, integral over omega naught bf dotted with w dv minus integral over the traction boundary t dot w dA. Okay, and now we've set epsilon equals 0. Okay, all of this equals 0, right? And the reason that this works is because partial of psi with respect to f evaluated at f epsilon, okay, and then epsilon equals 0 is simply partial of psi evaluated, partial of psi with respect to f evaluated at f, okay, since f epsilon equals 1 plus derivative with respect to x of u plus epsilon w, right? And here when we set epsilon equals 0, we simply lose this, right? And then we get back just plain old f. Okay? All right. So we've done what we set out to do. We've obtained the equilibrium condition for nonlinear elasticity. Okay? And that equilibrium condition is the following. It is integral over omega naught partial of psi with respect to f contracted with partial of w with respect to x, where w is a variation, dv minus integral over omega naught bf dot w dv minus integral over the traction boundary T dot W dA equals 0 for equilibrium. Finally, note, what is this one? What is partial of psi with respect to f? Psi is our strain energy function. Right? It's an object we've used very often and used widely, actually. This is our first Euler-Kirchhoff stress tensor P. Okay? So, this is our equilibrium condition. It is also often called the weak form of the balance of momentum Okay, it's a weak form of the balance of momentum for static problems. By static, we mean problems that are not dynamic, where the time-dependent term is missing. Okay, you observe that there is no time dependence in this problem, right? So this is often called the weak form of the balance of linear momentum for static problems. When we come back in the next segment, we will try to understand also at the end of that segment why it is that we call this the weak form of the balance of linear momentum. Okay? Right, we'll stop here.